Imagine stepping into a spacecraft knowing that when you return, your body will no longer be the same. Your bones, your muscles, your blood, your DNA, even the way you see the world, literally. Today, we are going to answer a simple and terrifying question. What really happens to the human body after an entire year in space? And this isn't a theoretical hypothesis, it has already happened. 3 astronauts board a Soyuz spacecraft. 2 of them are part of an unprecedented mission in the history of space exploration. American astronaut Scott Kelly and Russian astronaut Mikhail Kornienko set off to live on the International Space Station for nearly an entire year. During this period, the station receives hundreds of scientific experiments, but the most important experiments are themselves. Scott Kelly becomes even more special for a curious reason. He has an identical twin brother, Mark Kelly, who remains on Earth. Same DNA, same genetics, 2 completely different environments. While one lives in microgravity, the other remains bound to the planet's gravity. For the first time, scientists are able to compare, almost like a perfect experiment, the direct effect of space on the human body. The goal is clear: to understand if long missions, such as a trip to Mars, are truly viable. And the results are disturbing. The journey to the International Space Station is fast. In a few hours, the astronauts leave the Earth's ground and enter orbit. Technically, gravity still exists there, but because the station is constantly falling around the planet, the astronauts don't feel that effect. In practice, they spend an entire year in freefall. And the first few days are brutal. The first impact is space sickness. Our brain relies on various pieces of information to understand where we are: vision, the inner ear, the sensation of movement. In space, this information conflicts. Your eyes say you are still, your inner ear says you are moving. The result is nausea, dizziness, and in many cases, vomiting. Until the body learns to reinterpret reality, the discomfort is constant. Another immediate effect is growth. Without the weight of one's own body compressing the spine expands. Astronauts grow on average up to 5 centimeters in the first few days. It sounds curious, but it is accompanied by intense back pain to the point of requiring medication. And then comes something even stranger. In the first 24 hours, an astronaut urinates liters and liters of fluid. This happens because without gravity, the body's fluids redistribute. Blood rises from the legs and accumulates in the torso and face. The body interprets this as excess blood and tries to get rid of it. It's the beginning of a long chain of effects. After about a week, the body adapts to the new normal. The nausea subsides, the pain eases. But now the long-term problems begin. Without gravity, your bones stop receiving impact, and bones need load to stay strong. It's a basic principle of biology. The body eliminates what it doesn't use. In space, an astronaut can lose up to 2% of bone mass per month. On a 2-year mission, this could mean losing half of the bone's strength. And the worst part, this loss is never fully reversed even after returning to Earth. The muscles follow the same path. Without weight to lift, they atrophy. To combat this, astronauts follow a rigorous exercise routine, about 2 hours a day, 6 days a week. Special machines simulate resistance, but even so, profound changes happen. Muscle fibers reorganize. The body trades endurance for explosiveness. Even with intense training, there's a loss of mass and strength. Diet also changes. Astronauts eat about 30% less than they should, not because food is lacking, but because hunger decreases. Palate changes, the smell of food becomes less intense, since in space there is no convection of warm air. Additionally, digestive problems and changes in the gut microbiome are common. The result is continuous weight loss. And we still don't know if, on truly long missions, this could become dangerous. But perhaps the most fascinating and terrifying aspect lies in the DNA. Scott Kelly's DNA was not altered. The genetic code remained intact. What changed was the way that DNA was expressed. Genes that were turned off on Earth were activated in space. This changed which proteins the body produced, altering the organism's internal chemistry. Telomeres, structures associated with cellular aging, actually increased during the mission. This generated headlines suggesting that space rejuvenates astronauts, but the effect was temporary and reversed after the return to Earth. On the other hand, radiation is a serious problem. Even within the planet's magnetic field, the space station receives much higher doses of radiation. Scott Kelly was exposed to levels equivalent to several X-ray exams a day. The result was a significant increase in DNA replication failures, which raises the risk of cancer throughout life. Blood also behaves strangely. Without gravity, it pools in the face and chest. The so-called puffy face and bird leg syndrome emerges. The face becomes congested, the legs thin out. The pressure inside the skull increases. And this is where one of the most worrying problems comes in: vision. This increase in pressure can deform the retina and the optic nerve. Many astronauts report permanent vision loss after long stays in space. Scott Kelly was one of them. Today, this is one of the biggest barriers to long-duration missions. A definite solution does not yet exist. And recently, a new concern has emerged. A study published in the journal Nature revealed that the kidneys also suffer structural damage in space. In addition to processing the calcium released by weakened bones, they seem to lose part of their functional capacity. In animal tests, this even led to renal failure. According to the researchers themselves, if nothing is done, an astronaut could reach Mars but need dialysis on the way back. After 1 year, Scott Kelly returns to Earth. He returns weaker, with elevated inflammation, intense pain, and a constant feeling of illness. His body, unaccustomed to gravity, interprets its own weight as an aggression. The recovery takes weeks. And here is the most terrifying point of all. A year in space is approximately the time needed to travel to Mars. Everything you have heard so far would just be the one-way trip. The real mission would begin when the astronaut arrived at the red planet, already fragile. We still have a lot to learn before sending humans safely on such long journeys. But there is a positive side. Understanding how the body reacts to space helps treat problems here on Earth. Aging, osteoporosis, muscle loss, people bedridden for long periods. Space health ends up driving human health. Now I ask you, knowing all this, would you spend a year in space? Write it in the comments. If this video expanded your perception of the human body and the universe, leave a like. Subscribe to the channel to continue exploring the limits of science, space, and our own existence. Until the next video.